When performing stoichiometric calculations, we must always begin with the balanced equation. Consider the reaction between butane gas, C4H10, and oxygen gas, O2, producing carbon dioxide gas, CO2, and liquid water, H2O. When balancing equations, one should always proceed systematically. By that I mean, let's start at the beginning. In the compound butane, there are 4 moles of carbon. So we have a 4 on the left side of the equation, but a 1 on the right side of the equation, where carbon dioxide contains only 1 mole. To balance the carbons, we place a 4 in front of the carbon dioxide gas. Now notice that the coefficient 4 applies to the carbon, but it also applies to the oxygen in the molecules. It is very important to remember that. Students forget this so many times. Listen, if a coefficient is placed in front of a compound or a molecule, the number applies to all elements in that compound or molecule. Butane also contains 10 moles of hydrogen. So to balance the hydrogens, we have to place a 5 in front of the liquid water, because the liquid water, the molecules only contain 2 hydrogens each. So by placing a 5 in front of the liquid water, we now have 5 times 2 for 10 and 5 times 1 for 5. So we now have 10 moles of hydrogen on the right side. Now, at this point, let's consider the oxygen. On the right side, we have 4 times 2 for 8, plus 5 times 1 for 5. So on the right side, we have 13 moles of oxygen, where on the left side, 1 mole of diatomic oxygen contains 2 moles. To balance the equation, we must now double it. By this I mean, in order to balance this equation, we must now make the right side of the equation an even number. When doubling the equation, we double all species with the exception of the diatomic oxygen, which stands alone. So changing the oxygen changes nothing else except oxygen. Doubling the 4 moles of carbon dioxide gas now gives us 8 moles, and doubling the 5 moles of liquid water now gives us 10 moles. Now on this side, the right side of the equation, we have 4 times 2 for 16, plus 10 times 1 for 10. So we have 26 moles of oxygen on the right side now. And to balance the oxygens, we simply place 13 in front of it. CO2. Instead of 13 moles of oxygen gas, suppose only 5 moles of oxygen gas is available. How would that amount affect the other substances in the chemical reaction? This is called stoichiometry, and when performing stoichiometric calculations, first write down the molar ratio from the balanced equation. In this case, the molar ratio will be 2 to 13 to 8 to 10. Now, using the molar ratio, create a fraction where the fraction will always be x over check. Since we're given information about the oxygen gas, we place a check over the 13 in the molar ratio. All other numbers in the molar ratio will be given an x. Remember, the fraction must be x over check. So to determine the number of moles of butane gas consumed by 5 moles of oxygen gas, we write the following fraction. 2 moles of butane gas divided by 13 moles of oxygen gas. Now multiply this fraction by the given amount, which is 5 moles of oxygen gas. We can write it this way. Now, since moles of oxygen gas will cancel out, we will determine the number of moles of butane gas consumed. 2 divided by 13 times 5 is equal to 0.77 mole. Moles of O2 cancel out, so 0.77 mole of butane gas. To determine the number of moles of carbon dioxide gas produced, we do the same thing. Now we divide 8 moles of CO2 by 13 moles of O2. Multiply times the given, 5 moles of O2. Now, moles of O2 cancel again, and we're left with moles of carbon dioxide gas, and the number of moles of carbon dioxide gas produced will be 1.55 mole. Okay? Now finally, for the liquid water, 10 moles of H2O divided by 13 moles of O2 times 5 moles of O2 will equal 1.92 mole of H2O, the liquid water. Notice also, in this particular case, moles of O2 cancel. And it's as simple as that.